Okay, thanks everyone. It's a pleasure to be here, and thanks for the invitation to speak at this event. I've been seeing posters for this event for the last several years, and I've not been able to go, so I'm very happy to be here this year, um, if not only in two dimensions. But um, before I start my talk, I wanted to just dedicate it maybe to the memory of two great mathematicians who died due to COVID-19. So maybe one is very well known, John Conway, um, and the other is Ray Hubler, who was a mathematician at CUNY Graduate Center, and he was a major figure in the field of Brouwer groups. He worked on a lot of questions surrounding the purity conjecture for the Brouwer group and the difference between the cohomological Brouwer group and the Brouwer group. So I just wanted to mention that. All right, so classical Hasse-Minkowski. Um, this is a theorem that we teach in a lot of, maybe at the end of a course on class field theory, or maybe at the beginning of a course on quadratic forms. It says that if you have a non-degenerate quadratic form Q, and it's over, say, the rational numbers, then, and by non-degenerate quadratic form, here by quadratic form, I'm just meaning that we have, it's a homogeneous polynomial of degree 2, and non-degenerate means that the associated symmetric matrix you can form is non-singular. And one thing we're interested in is about the non-trivial zero. So of course, if it's a homogeneous form, so if you plug in 0 for all the variables, you're going to get 0. But we're interested in non-trivial zeros. And the statement is that if the quadratic form has a non-trivial 0 over R and over QP for every prime P, then in fact, the quadratic form has a non-trivial 0 over Q. So this is an R here in the QP you might recognize as being all of the various completions of the field Q, and we'll get to that in a second. But one nice way, and the way in fact that Minkowski, who proved first this version of the theorem, actually stated it, is if you assume that Q is primitive, so assume that the coefficients of the quadratic form are all relative, they're all coprime, then what does Q having a non-trivial 0 locally, it just is the same as Q being indefinite as a real quadratic form and just having a non-trivial 0 over Z modulo n for every n. So of course, if a quadratic form has a 0 over Q, then it will have a 0 modulo n for every n. But if conversely is the statement, it's this direction that is very interesting. So this is kind of a standard classical, what we call local global principle. And in fact, it's more generally true, not just you can replace the rational numbers by any global field, so a number field or a global function field, so finite extension of Q or finite extension of FP of T. These are the types of fields that come up in class field theory. And so you have the same statement where now you can say that if Q has a non-trivial 0 over the completions at all places of K, then in fact Q has a non-trivial 0 over K. Okay. And even more generally, you could ask, or you could just have as an idea for a possible theorem, you have a field K, you have a set of discrete valuations, and you have for each discrete valuation, you have the completion, and you might ask about the local global principle for isotropy for quadratic, namely that if you have a quadratic form, a non-degenerate quadratic form over K, you might ask whether being isotropic, so isotropic is a fancy quadratic form theory speak for just saying has a non-trivial 0, so you could ask whether the quadratic form being isotropic over every completion implies that it's actually isotropic over our base field. And the examples here where we take kind of the set of discrete valuations, say all discrete valuations, and we're no longer talking about, say, places or Archimedean valuations, then Hasse-Minkowski provides an example of this local global principle. If, for example, K is a purely imaginary number field, then there are no Archimedean places to worry about, and then you just have to check it at all discrete valuations. Or if you have a global function field, then this is this classical statement of Hasse-Minkowski. Okay. There are various ways to generalize this statement. So there is one way, which you could ask for quadratic forms. You could ask for local global principle for quadratic forms over kind of arithmetic fields of interest. So you choose K to be, instead of a number field, say a function field of a variety over a number field. So some nice counterexamples that come up in the literature are first due to Vid in the early 30s, that he presents some failures for the local global principle for quadratic forms, for ternary quadratic forms, so quadratic forms in 3 variables over function fields of conics. So here's an example that he gives in his paper. So he doesn't actually, in the original paper, this is not how he states it. He's talking about a failure of a local global principle, of a norm principle for the existence of, he's asking whether, a -1 is a sum of 2 squares, for example. And so this is a standard application of Hasse-Minkowski, is showing that if something is a sum of 2 squares locally, then it's a sum of 2 squares. But here you might ask whether that's true over more general fields, and here was the example that it gave, or somehow translated into this language, that that x squared plus y squared plus z squared over this field. So you would join a transcendental variable to Q, and then you would join this additional rational function, square root of -21 minus t squared. He showed that this quadratic form is everywhere, has 0 locally for every completion at every discrete valuation of this field, but actually that this is an anisotropic form. This has no global 0 over this field. Castles found examples of quaternary quadratic forms, so quadratic forms in 4 variables over a rational function field over Q. So these are quadratic forms whose coefficients involve rational functions, and that over every completion, so over at discrete valuations, those which are trivial on Q and also those which are not trivial on Q, he found such examples. And then there's work going back to, I don't know, Castles, Ellis, and Pfister, that they show that there are kind of counterexamples for the local global principle for, again, quaternary quadratic forms over, say, a 2-variable function field over the real numbers, if you're interested in such fields. So this is one way to generalize the question of the local global principle, and it's false. I mean, there's all kinds of counterexamples. So the interest then becomes over which types of fields are we interested in, and are there counterexamples to the local global principle? And maybe you might ask, in what number of variables do those counterexamples come up? So those are some interesting questions you could ask. Another way to generalize this question is to systems of quadratic forms. You could ask, okay, now I don't just want one quadratic form to have a 0. I want, say, a pair of quadratic forms to have a non-trivial 0. So if we have a pair of quadratic forms on the same underlying, K vector space W, then we might ask, so this kind of statement of the local global principle, that does there exist a common vector over every completion? If that happens, then does there exist a common isotropic vector over the field? So this is something you might ask, and in fact, castles in that same work, or you can translate them in both ways, and we'll see in a second how. But that same work kind of provides examples of the failure of the local global principle for pairs of quadratic forms in 4 variables over the rational numbers. So already, even if you're not interested in fancy function fields, then you might be interested in this question of pairs of quadratic forms, and there are counterexamples to the local global principle. And one nice statement, there's not just kind of some examples out there, but in fact you can take some work of Bhargava and Shankar on kind of the 4 Selmore groups of elliptic curves, and in fact you could from that deduce that the local global principle, in fact, fails for a positive proportion of pairs of quaternary quadratic forms. So this is not just something that happens very randomly. It also holds for a positive proportion of pairs of quaternary quadratic forms. Okay, so another way to generalize, which is maybe more commonly seen in kind of in survey texts on Hasse-Minkowski, is to higher degree forms. And so everybody mentions this famous example of Lind and Reichardt for, say, quartic forms. Say this is a non-homogeneous, but it's a quartic form for which has this is a quadratic form over the rational numbers. I mean, this is a quartic form over the rational numbers that has a that does not have a global non-trivial 0, but has everywhere locally, p-adically, and real zeros. And then, of course, everybody loves to mention this famous example of Selmer over the rational numbers, 3x cubed plus 4y cubed plus 5z cubed. It's a homogeneous cubic form in 3 variables that is a failure for the local global principle. And again, even earlier work of Bhargava and Shankar, that this local global principle for, say, cubic forms in 3 variables fails for a positive proportion of such forms. So these examples are out there. Once you go above forms of degree 2, in terms of degree or in terms of complexity of the field, these counterexamples start to pop up. All of these counterexamples one can reformulate kind of geometrically as a local global principle for the existence of rational points. So this is, if X is a smooth projective, say, geometrically integral variety over a field, over our favorite field K, then we might ask whether the existence of rational points for all completions implies the existence of rational points. And so one way of actually this is just a reformulation of the various previous examples. For example, if you take the variety to just be the projective hypersurface defined by those homogeneous forms, then this local global principle for rational points exactly translates into the local global principle for isotropy that we discussed before. And if you take X to be the complete intersection, say, of 2 quadrics, then this is just, then the local global principle for rational points on such a variety is equivalent to the local global principle for pairs of quadratic forms. So this is maybe a nice geometric way in terms of rational points to sum up those previous attempts at a generalization of the Hasse-Minkowski theorem. Okay, so there are various links between these, and one of the links that exists between these is a theorem which is commonly called the Ammer-Brummer theorem these days. It's got a long, interesting history, and there's a survey paper by David Leap which explains this history, but I'll just refer to it as Ammer-Brummer. So the theorem is as follows. It's a theorem about quadratic forms. It says that if K is a field, and if you have a pair of quadratic forms over that field, then in fact that pair is isotropic. So in the sense that we had before, that pair has a non-trivial common 0, if and only if that the quadratic form that you would form by introducing a new transcendental variable t and taking Q1 plus TQ2, and thinking of that as a quadratic form over the field of rational functions over K, whether that is isotropic over that field. Certainly one direction is very obvious. If you have a pair of zeros, then, I mean, if you have a common zero to the two quadratic forms, and you just plug that same common zero into V and you'll get zero. So this is the hard part is imagining that just the existence of an isotropic vector for this quadratic form, this vector may not only consist of elements of the field. It may not be a constant vector. It may have t's in it and rational functions in it, but the existence of such a vector apparently implies the existence of a common solution to the pair. And now, translated geometrically, what is this saying? This is saying the pair having a common isotropic vector means that complete intersection of the two quadrics has a rational point. And sorry, I don't know what this F is here. This is a K. It says that this variety, which is the complete intersection of two quadrics, has a rational point. So that's what this side says. And this other side is something much stranger. It says that, well, we can view this equation as a pencil of quadratic forms. So this is we can kind of think of it as a moving family of quadratic forms that are parametrized by the base P1, and in fact, geometrically, we can think about that as a so-called quadric fibration. So this is a quadric bundle, if you want, or it's just a pencil of quadratic forms. But then, as a quadric bundle, you might ask whether this map to P1 has a rational section, and the existence of such a rational section is exactly equivalent to the existence of an isotropic vector here. So these two statements, whether some complete intersection of two quadrics having a rational point, and on the other hand, whether some pencil of quadrics having a rational section, these are actually equivalent statements by this Ammer-Brummer theorem. And here's an example of this working out. Say if you have a pair of quaternary quadratic forms over the rational numbers, so in the situation that we were looking to, then if we look at the complete intersection of those two defining quadrics defined by the two quadratic forms, then in fact, this is well known. This is an intersection of two quadrics in P3. This is a genus 1 curve. Right? It may not have a rational point, but it has some Jacobian, which you could call E. And so for example, one nice example is that if you take the pair of quadratic forms in 4 variables, they look like they have 3 variables. So the variables here are x, y, z, and w, but in fact this quadratic form here is only in 3 variables, and this quadratic form here is only in 3 variables, but in total you have 4 variables, so they're sitting on this common vector space. Then if you take these 2 quadratic forms and you form the complete intersection of 2 of them, that's a genus 1 curve. It's given by 2 quadratic equations. But for any genus 1 curve that's a complete intersection of 2 quadrics like this, there's a so-called Jacobi form for that genus 1 curve. It's a quartic, homogeneous quartic of this type of shape. It's a weighted homogeneous quartic with this shape. So this is the so-called Jacobi form of the complete intersection. And in fact, the Jacobi form for this X that you get is precisely the Lind-Reichart example that was mentioned before. So you see that on this pair of quaternary quadratic forms, there is no common solution, because such a common solution would be a rational point on this genus 1 curve, but this genus 1 curve, we know since the 1940s, does not have a rational point. On the other hand, it does have local points everywhere, this genus 1 curve, and hence this pair of, by the Ammer-Brummer theorem, hence this pair of quadratic forms has a common isotropic vector everywhere locally. So to sum that up, in fact, because this X is a genus 1 curve with Jacobian E, we can view it as an element of the Tate-Shafarevich group of E, of its Jacobian. And in that sense, and it's, well, assuming that it's everywhere locally solvable, we can then view it as an element of the Tate-Shafarevich group. And the assumption that that class is a non-trivial class, so that genus 1 curve does not have a rational point, is then equivalent, so this is Ammer-Brummer here, to, well, or this is not Ammer-Brummer. This is just a statement that complete intersection, point on the complete intersection is equivalent to a common isotropic vector. So these two are equivalent. So the fact that this class on the Tate-Shafarevich group is non-trivial is equivalent to this pair of quadratic forms, in fact, being a failure to this local global principle. I don't know why this I is here. Oh, and this one too. And now here, then, this failure of the local global principle for this pair of quadratic forms is that equivalent, and here we're using Ammer-Brummer because we're relating the existence of an isotropic vector on a pair to the isotropy of this pencil, that this pencil here has is a failure to the local global principle over the field Q of T. And there's a little bit of extra work here, in fact, and this is why you somehow need to use all local places. So in fact, in this step here, you really need to use also Hasse-Minkowski, because you're also needing to avail yourself to discrete valuations that are non-trivial on Q, and then you need to look at completions and so forth. So, okay. But this is what I wanted to say, is that the kind of the takeaway of this geometry, this connection geometry and Tate-Shafarevich group and quadratic forms, the takeaway here is that somehow the failure of this local global principle for quadratic forms somehow seems to be related to or controlled by some type of auxiliary object of interest. So in this case, the failure of the local global principle for a quaternary quadratic form over a function field, rational function field over the rational numbers, is related to the existence of a non-trivial element on a Tate-Shafarevich in a Tate-Shafarevich group. So yes, Armand here is in the audience. Nice to see you, Armand. All right, so I think that motivates potentially this takeaway here, at least for me, motivates the study of local global principle for quadratic forms over various function fields. And you could take function fields of, we can assume they're function fields of smooth projective varieties over our field K, which maybe we could take to be a number field, a local field. We could do all kinds of things. But let's just step back for a second, and you might ask, well, maybe the easiest case, in question mark, is that the field is just the complex numbers. This is a field of some arithmetic interest. It's not an algebraically closed field, and so maybe we should be doing arithmetic geometry over function fields of varieties over the complex numbers. So okay. Let's take kind of what you might think is the easiest case. K is the complex numbers. X is a curve, so a one-dimensional complex variety, and K is its function field. Then, if you just easy application, Ammer-Brummer and just Hilbert-Nilsstellensatz will show you that if you any such pencil like this over the rational function field will be isotropic, because as long as we have at least 3 variables, because in that case then the intersection of these two quadrics defined by the quadratic forms is a positive dimensional complex variety, and hence has a rational point by the Null-Stellensatz. So this is a statement that kind of combining these two things shows that any pencil like this over C of t is isotropic if this pencil has at least 3 variables. But in fact, more generally, as a result of Then's theorem, any quadratic form in at least 3 variables over a function field of a curve over the complex numbers is already isotropic. Okay, so that's one thing to know about quadratic forms over such fields. In 3 or more variables, they always have a 0. Okay, but what about in 2 variables? There we don't, we might have a hope at the local global principle. And there, the theorem you can prove, it's not I don't know who first noticed this, but the theorem that you can prove is that the local global principle for binary quadratic forms, then in 2 variable quadratic forms in 2 variables over such fields, holds if the genus is 0 and fails if the genus is positive. So since we're over the complex numbers or an algebraically closed field, of course, being genus 0 means that the x is P1. But this dichotomy here is again one of these very classical important dichotomies in arithmetic geometry when you're talking about the theory of curves, where somehow genus 0 and then genus higher have very different behaviors. So, and I want to get back actually to why it is that there's a failure of the local global principle for binary forms in higher genus. I'll say right away that for genus 0, in fact, you can prove this quite handily using, there's like a Milnor exact sequence for quadratic forms for the Witt group for rational function fields, and this somehow shows this at least part. But I can tell you a more satisfactory explanation for this in a second. All right, let me state one theorem, which is kind of going on generalizing this case, which is that, in fact, this case here, where the local global principle for binary quadratic forms holds over a complex rational function field, is the only case, in fact, where the local global principle for quadratic forms holds over a complex function field. So more generally, this is a theorem that I proved with Suresh, beginning in various iterations, various versions in 2017, and then up through this fall, in fact. We proved that if K is an algebraically closed field of characteristic 0, so say, for example, K is the complex numbers, and big K is a finitely generated field of transcendence degree n. So you just should think yourself K is the function field of X, where X is a variety of dimension n. Okay. Then, in fact, the local global principle for quadratic forms fails for quadratic forms in fact 2 to the n variables over that field, except in the one case when you have a rational function field, and then we've seen already that it holds. Okay. But in all other cases, so if your function field has transcendence degree 1 but is associated to a higher genus curve, or if you're any variety function field of transcendence degree 2 or higher, there are counterexamples to the local global principle, and we can in fact find them in 2 to the n number of variables. And let me point out about this 2 to the n variables is that this is kind of the border case when you might ask for counterexamples to the local global principle. Similarly, as in the transcendence degree 1 case, there's a kind of a generalization of Then's theorem, which is the so-called Then-Lang theory, which implies that any such field, a function field of transcendence degree n over an algebraically closed field, is a so-called CN field. And the CN fields have the property that any quadratic form in greater than 2 to the n number of variables is already isotropic. It already automatically has a 0. And so you might think 2 to the n variables, it's kind of the first case where you might ask for there to be a counterexample to a local global principle, and in fact we find them. Okay. I'll move forward. Let me just tell you a quick history about this theorem. So the transcendence degree 1 case is what I stated before, and really let me give you a quick sketch of the proof there. So in the transcendence degree 1 case, if C is a smooth projective curve over our algebraically closed field K, then in fact the local global principle for binary forms in general, it's the general statement, the local global principle for binary forms is equivalent to the so-called global squares theorem. So you might ask, this is another type of local global principle. If you ask, is an element in a field a square if it's a square everywhere locally at all completions? So these two are equivalent. If the global square theorem holds, so if it's true that being locally a square implies that you're globally a square, then that in fact is equivalent to the fact that the local global principle for isotropy holds for all binary quadratic forms over that field. But being a global square, think about we're on a function field of a curve, and having a function which is a square everywhere locally but not a square gives you, in fact, the divisor of such a function. It gives you an element in it's a 2 torsion element in the Picard group of the curve. So it's an element of pic 0 C, which is 2 torsion. And hence, if we're assuming that the local global principle in fact always holds, then that's equivalent to this pic 0 2 torsion being trivial. And of course, this only holds if C is P1. Otherwise, over an algebraically closed field, we certainly know that any higher genus curve has, at least a large number of, has at least some non-trivial 2 torsion in its Picard group. So this is somehow a geometric explanation. But again, I want to point out that somehow the failure of the local global principle for quadratic forms is, again, controlled by something. So it's a 2 torsion point on the Jacobian. So that's the transcendence degree 1 case. The transcendence degree 2 case, there was a paper due to Kim and Rush in the early 90s, which was later kind of elaborated by Bevilacqua in 2004, which proves this theorem over over the rational function field in 2 variables over the complex numbers. And I write here Hilbert's 10th problem, question mark. There's a strange history here, which is that Kim and Rush, these 2 mathematicians are really working in logic. They were proving around this time lots of theorems about Hilbert's 10th problem. Hilbert's 10th problem is the question of whether a Diophantine equation or a system Diophantine equation whether there exists, say, an algorithm to decide the solvability of it over the integers. It's not how Hilbert stated it, but it's equivalent to what Hilbert stated. And is there a procedure, a first order procedure, to decide the existence of a solution to a Diophantine equation over the integers? And this is proved that Hilbert's 10th problem has a negative solution. It's a famous work in logic terminating in the work of Maciejewicz, but it's still open, notably over the rational numbers. We still do not know whether a system of polynomial over the rational system of polynomial equations over the rational numbers, whether the existence of a solution, there's an algorithm to decide that. So that's a very interesting problem. But these 2 people wrote a series of papers on generalizations of Hilbert's 10th problem, to various types of other fields and other rings, various number rings, various function fields over p-adics, over complex numbers, and in particular, they handled Hilbert's 10th problem for this case. And in the middle of that series of papers, all of a sudden, there's one paper on the local global principle for quadratic forms. So it begs the question, is there some relationship between these two problems? If you have any ideas, you can let me know. In a paper of myself with Parimal and Suresh going back to 2015, in fact, we didn't even know about any of this earlier work, but we had proved it for over any algebraically closed field of characteristic 0 and and S is any surface, so any function field of transcendence degree 2. And then in work of mine with Suresh, in kind of probably the first version of what we did, we proved this for a purely transcendental function field over the complex numbers. And so that's where it stood up at least until 2017. Let me give you a quick sketch of the proof in at least the transcendence degree 2 case, because it'll give you a little flavor. So first, we prove some kind of geometric presentation lemma, which says that if we have our function field and it's the function field of a smooth projective surface, say, then we prove that either that surface admits a quaternion algebra, which is non-zero and is unramified. So this is an unramified element in the Brouwer group, and an unramified two-torsion element in the Brouwer group of this surface. Either that exists, or if not, for example, like projective space or project P2 does not have any unramified quaternion algebras, then there exists some finite flat double cover where Y is smooth, projective, and there does exist such an unramified quaternion algebra, non-zero unramified quaternion algebra on that Y. And a kind of probably standard example is X is P2, the Brouwer group is trivial, but if we take a 2-to-1 cover of P2 branched along a sextic, that's a K3 surface, which is very well known to have lots of unramified Brouwer classes. Then we form the so-called, I don't know, twisted norm form. So if, in fact, if we're in the first case and we have an unramified quaternion algebra over X, then we can just take the norm form of that quaternion algebra, and it's definitely anisotropic because the quaternion algebra is non-split. Yet it's locally isotropic because of the fact that this algebra is unramified. Or somehow locally the isotropy can be measured by these residue maps, and the residue maps for an unramified form are 0 because the form somehow has good reduction. These residue maps are all vanish, and so this is an example. But if we don't have such quaternion algebras over the field, then we have to take this double cover Y to X. This is a 2-to-1 double cover, and in that case, let me write L here is the function field of Y, and it's a quadratic extension of K, so we can write it as K adjoins square root of D for some D. And then what we can actually prove is that taking any quaternion algebra over this field, over this surface, unramified quaternion algebra, in fact, we can show that we can actually choose the functions that form the quaternion algebra to be lying in the base field K, not in the function field of Y, but actually in the function field of X. And there's a little argument here using the restriction co-restriction sequence and the existence of a map, a co-restriction map on the level of the unramified Brouwer group, going back to work of Deligne. And then we form then this kind of twisted norm form. It looks like the norm form of the quaternion algebra A, except it has this D thrown in. This is a quadratic form over the field K. And again, it's anisotropic for the same reason. If we go back up to the function field of Y, then it looks like a norm form, and this element is non-zero. So, and then it's again locally isotropic because it's not unramified now over K, but at least this part of it is unramified, and that's enough to actually deduce the local isotropy. And what about the higher transcendence degree case? So what is somehow what's the relationship between these? Well, if you think back in transcendence degree 1, we used kind of two torsion elements on the Jacobian. In transcendence degree 2, we used two torsion elements on the Brouwer group. And in transcendence degree n, it turns out the construction involves two torsion elements on this so-called nth unramified cohomology of the function field. And here I give you its definition. It's very reminiscent if you've worked with the unramified Brouwer group. It's very reminiscent. You take your Galois cohomology group in degree n, and then you have these residue maps, which are generalizations of the usual residue tame symbol residue homomorphisms that you have on the Brouwer group, and you land in this Galois cohomology group of dimension 1 lower with over the various residue fields of your discrete valuations, and then you're looking at the kernel, the simultaneous kernel of all these residue maps, and that's your so-called higher unramified cohomology. And I'll just say that we kind of understand this, but this higher unramified cohomology is very mysterious. And already, in particular, in degree 3, it's related by some work of Coliotelin and Voisin, it's related to the integral Hodge conjecture for codimension 2 cycles. So if you find non-trivial elements in this H3 unramified group, very often these can manifest themselves as counterexamples to the integral Hodge conjecture. So this is a theme that's been taken up very recently. All right, let me. Yes.
Sure.
Yes.
We started a few minutes late. It's about 10:45.
Yes, I see that. Yeah.
Go ahead and take like 2 or 3 more minutes or
Perfect.
so.
Perfect. That's
Okay.
what I need.
Perfect.
Yeah, and my timer here I have 2:45. Okay. So in our case, in fact, we don't end up having this. We don't have any kind of geometric presentation lemma for unramified cohomology, but we use this trick due to Bogomolov, which is kind of amazing, and I'm trying to popularize this trick, so I want to tell you about it. So that if you have a function field of transcendence degree n, at least 1, over, say, an algebraically closed field, but more generally this works, then in fact, this is not just Noether normalization. You can always find the function field as an extension of a rational function field, but you can always choose that extension to be of odd degree. This is an amazing trick. If you want to know more about this trick, I can tell you later. But then you use Springer's theorem that says that if you have a quadratic form and you have an odd degree extension, then the odd degree extension does not hurt the non-existence of a zero. If you have a quadratic form that's anisotropic over a field, then it remains anisotropic over your odd degree extension. And so what we get from this trick of Bogomolov and Springer's theorem is that if you have a failure to the local global principle over a purely transcendental field, then bringing it up to your function field via an odd degree extension, you will get a failure to the local global principle K. So we've essentially reduced ourselves to just working over the purely transcendental extension. Finally, let me just tell you where the products of elliptic curves come in. What we do is we then give ourselves the following situation. We have n elliptic curves. We take each one we view as a Legendre equation, and then we take their product, and that's kind of the Legendre equation presents our curve as a Z mod 2 cover over P1 with 4 branch points, and we take the product. It's now a Z mod 2 to the n cover of the product of P1s. And in fact, inside of this, there's an index 2 subgroup, and so by Galois theory, the index 2 subgroup where all the vectors add to 0, and we get this variety Y, which is itself a Z mod 2 cover of P1 cross P1 cross P1. And this Y has an equation of the form like this. It's like a Weierstrass equation, Y squared equals a product of kind of Legendre equations for different variables. Okay, this variety has come up in all kinds of ways. So in fact, in n equals 2, this variety admits a nice resolution, which is in fact the Kummer K3 surface associated to the product of elliptic curves. And for n equals 3, this came up as kind of a Calabi-Yau three-folds of various types. And let me just tell you what we're interested in. So we need to construct unramified cohomology elements on this product of elliptic curves. And what we end up doing is having to prove a version of a theorem that was proved by Gabor over general fields, like for example, over a number field. And this is the theorem we end up proving. So prove a theorem about the existence of various unramified cohomology elements on products of elliptic curves over any discretely valued field. And this is the situation in which these curves come up. We need them to have non-integral J invariants. And I'll just leave you with this last question on the slide, as maybe people have questions. Okay, sorry for going over. Thank you.
Yeah, no problem. Let's going faster. There's one question